Hello, dear colleagues and participants. My name is D.Larionov. I am with the AI team, the Cifrum Digitum, Cifrum company with Skoltech and Rosatom. We will talk about the important aspects of implementing oncology data analysis platforms and applied research for this area. So tumors and cancer are the second reason for death in worldwide after the heart diseases, and in 2019 we had 300,000 people dying from oncology, and this is 2 times less than heart disease, but 3 times more than the other reasons that are on the third place. So medical community has achieved huge progress in curing different diseases, and you can see on the slide the progress of for some oncology disease, like in lung cancer. We still have less than 5% of probability to cure the lung cancer if we mean the 5-year mortality. The amount of clinical clinical research is growing. So the key question is, how do we decide on the therapy methods for different patients? Those standards define this somewhat average probabilities, and one person cannot have all the needed amount of data to make the best decision. So the trend currently in oncology is personalized medicine, when in terms of IT you can define it as therapeutic approach based on both the historical data and genome data, and of course using ML and AI. A critical aspect of applying AI here is the data. In medicine, that can be text, the time flows, different images, but not all medical data have the same scientific value and usefulness. We can think of them as being accumulated within medical information systems or registries that are well represented within oncological centers. But if you look deeper, you can find that those systems are often aimed at just providing formal statistical reporting, like bed count or financial analysis. So there also are differences between the systems that can be used for intellectual data analysis and classic registries. Some of those differences are formalized on this slide. So completeness and truthfulness of data. If we work with the aggregator, then we can broaden the capability set. Retrospective analysis capacity gives you an option to also analyze and take into account the impersonalized parameters, and it gives us new potential, new opportunities to use it. And an international classifier for oncology is a TNM set of rules that allow you to stage the oncological illnesses, and they take into account different physical parameters like the size and whether it penetrates to other structures, metastasis, and other roles. They're different for different localizations and for different types of tumors, and this is getting worse because those rules are being reviewed like once in 5 years. So when you cannot unify that data, it means you cannot compare it across the time scale. And this means that you need to take into account the primary parameters and interpret them in terms of the different standards that were in effect during different times. So this means that the functionality and the IT system should be quite complex. So taking into account that problematics, and as part as our work with Herson's University, we have created a platform to analyze oncological data, and starting 2017, we work with this platform together with different centers. It helps work with patients, with surgery and chemotherapy with a number of localizations. And we broaden this spectrum for both localizations and the treatment profiles, and of course our main belief is that such platforms will be the fundamental for the decision-making support systems and personalized medicine. So to be more specific, here are the tasks you can solve based on that platform. And those are things like analyzing medical texts. The source data here can be, for example, surgery protocols, and we can annotate it by the data entered into the system by the user. You can use this to formulate a task in terms of machine learning, and the models you get from it can be transferred using transfer learning method to other areas. Second method would be predictive models based on the patient data, and that data are different. It can be anamnesis, complaints, treatments, surgeries, and so on and so forth. And based on the dynamic data, when you call the patient 3, 6, 12 months after some treatment and ask if something has happened, and all the potential factors. So the analytical power of that data is super high, but unfortunately they are not gathered as a system. And of course, statistical checking of the medical hypothesis, correlational analysis, the hypotheses that you find there are very important. So main players are the Herson's University and D.Dilov's computational image team that is joined in 2018. Some interesting results were already received, and Dmitry will talk about them in the second part of the presentation. And starting 2020, we have private entity Cifrum taking part in this. We are doing the commercialization of this product. And Dmitry Dylov will talk more about the commercial part of the product. Thank you. Thank you indeed for the introduction and for the invitation to present here. I am the leader for the informational imaging team in Skoltech, and I'm responsible for biomedical analytics. To get you an idea of what we do, it's computational imaging when we use some algorithms to restore the images, and computer vision and medical vision. to help understand medical images. As Denis has already pointed out, for such images can be actually very important for improving the machine learning, because as we already have that data, we can not only solve the task like here with a bladder, and as many of you have suspected, for segmentation tasks we try to apply the net architecture, but those who know how hard it is to define those convolution cores and convolution kernels to detect the pixels you need and take the pixels that would belong to the class. And here you need to detect the bladder wall and the bladder itself. So for the doctors, the description of the characteristics is super important. So we have numerical description. So actually we took this from physics, from computational imaging. So to say that if your convolution core resembles the object, then segmentation will be easier to make. So the convolution kernel needs to be similar in the form to the tumor. So we have a lot of state-of-the-art models represented here for segmentation, but if the model that we have contains those convolutions, convolution kernels that are formed in the needed way, we have very good results. And we called it the LORC method because it resembles the object. So we know how to solve this for existing database. Also, an important resource here is the Chernobyl registry, which is in the Herson's Oncology Institute, and we are talking about future. In 1986, after the explosion, they started to receive patients, one of them in Moscow, being Herson's Institute. And they have a huge pack of documents that have, according to the 1986 standards, they have those genetic research on the chromosome and cell damage caused by, with the data about how far the patient was from the epicenter. And thus, instead of animals, we have people in this clinical trial, and we have a lot of data on this. So the data depicting this is now here. It's very important. We can calculate that distance with a very high accuracy. And what we do is now we actually digitize it and try to find the amount of radiation that can be optimal for killing the tumors when you have just enough radiation to destroy the tumor. And it's super important for us, the mathematician, to get those 1986 standards. Now we have thousands of biomarkers instead of 16, but the question of what we can do here and how useful this information is an open one. So here's another example of how we can use the existing database to not only help the oncology patients, but to learn the new mathematical models and to structure the database, what Dennis has said. The global vision here is a worldwide trend. Everyone does this. We need to actually start doing this in Russia. This is called federated learning. And those two curves show you, the first curve shows neural net training on the data, and the second one, federated data. It lags starting from the first one, but it catches up fast. So the hospitals don't share data, and the data stays within the hospital. But because of that federated system, they can additionally train the models using the models and data. You actually exchange models, the bricks, additional learning for federated learning bricks from what the other hospitals can provide. And the data privacy is still pursued, so everything is okay in terms of privacy, and but still you can improve the results here. So because of the partnerships we have unique data monitor the development of this project to and see that those three business lines are super important, starting from intellectual analysis and AI implementation to ensure that we can solve those oncological issues with finding the correct solution for this specific patient. And this is something that our system allows to do. So thank you indeed for your attention. Those are the two addresses we have, and we'll be super happy to work together with you on this project.